Hello, class. I wanted to start off talking about our first unit that we have. And this unit will discuss the importance of vectors and scalar quantities and how they work in physics. This is not a very complex topic. You just simply need to somewhat pay attention and you will be able to understand what's going on here. The first thing that's important is a definition. In order to understand what's happening, you must be able to identify what a vector is. A vector is a variable that has both magnitude and direction. There's two important parts to this, but one part that's really important that may be a new term to you is this word magnitude. And what magnitude simply means, it means that it has a value. So that's not really complex. So, for instance, if my son was 36 inches tall, that 36 inches is a magnitude. If I say that I had $100, that $100 would be a magnitude. It's simply a value. So that's not a very complex thing. It's kind of a different word to describe like something having, a value to it. The other point that's important about a vector is that it also has a direction associated with it. So, and that association for the vector is usually symbolized by an arrow. We call this a vector arrow. This is not a very, complex topic. So, when I was a kid, I used to draw like little characters. I may draw like a little stick man, and I would say like this stick man, I want to show that he was running. And in order to show that the stick man was running, what I would do is that I would put an arrow going that way. That was a vector. And that vector, and this aspect, what changes inside this course is the longer the line, the faster he's going, or the further he goes. Those aspects are important. So, things that can be represented in which they have magnitude and direction, those things are vectors. And there's a lot of physics vectors that we want to talk about. Okay. On the other side, if something is not a vector, it's what we call scalar. It's a variable that has magnitude only. Excuse me. So what's important about that is that this one only has magnitude. Scalar quantities only have magnitude. They do not have directions to them. You say like, well, what could that be? Well, things like, for instance, volume. Volume. If I ask you like the volume of water, and I say this like I have 2 gallons of water, it doesn't have a direction to it, because volume is not a variable that has a direction to it. So if a direction is not associated with it, or I do not give a direction to it, it's a scalar quantity. If a direction is associated with it, it's going to be a vector. So, and can get kind of tricky. So I'm going to give a couple of examples to help you out to talk about scalars and vector quantities. So I'm going to make a table. In this table, I'm going to separate the difference between the two. I'm going to talk about vectors and give examples of those, and then I'm going to go scalars on this side. So vectors, example of it would be distance. I mean displacement, I'm so sorry. Okay. A displacement shows how far away are you from your original point and in which direction you are. So, for instance, when I drive to work, I drive southwest. So if I knew the distance, let's say it was 30 miles, I'll say I'm 30 miles southwest of where I was before. That's how much I'm displaced from my original starting point, which would be my home. In the case of a distance, it really doesn't matter. I always tell people a good example of distance versus displacement is that distance is like the odometer on your car. It does not care if I go to work and back home and back to work and back home. It keeps adding up numbers. The numbers that it adds is a total distance for that particular engine that's inside of that vehicle. Another vector would be velocity. And velocity is kind of like speed, but it's simply exactly what a vector is. It's speed with direction. It's me saying that I was driving to Dallas heading north at a speed of 65 miles per hour. In that case, I'm telling you how fast I'm going, my speed, but I'm also giving you a direction. The scalar quantity of that will simply be what we just spoke about, speed. Then we have acceleration, which is a vector. Force, which is also a vector. Now, this is also a really simple aspect because forces are generally going to be represented by an arrow. So, like for instance, if I was going to say someone was going to push a button, that's their hand, and here's my button. Okay, I would draw an arrow to symbolize that force. Momentum, some of these words you may not know. You will definitely learn them over time. And then let's go look at the scalar side. We have speed, we have distance, we have time. Time does not have a direction to it. We have volume. That's like the gallon of water situation that does not have a distance associated. I mean, a direction associated with it as well. So these are good starting point for examples. Vectors have directions to them that can be symbolized with a vector arrow, and scalars are not symbolized by a vector arrow. So those things are important. If I was going to talk about like just these two that are going to be real highlights for us later, displacement versus distance, a good example that we can use is someone running around a track. Let's say like the track on the football field, around the football field behind the field house. That person may go here and run all the way around that track. And I know that this total distance is equal to 400 meters. However, that person started off from this point and it ended at that exact same point. So their total displacement is actually 0 meters because they finished exactly where they started at. So that's the aspect of like how distance and displacement and how some vectors versus scalars and how those two things work inside physics. Some things that are important is that we can add up different type of vectors. So I'm going to use a distance or displacement example for our start. So let's say I have my same stick man. And my stick man, he walked this way. Let's call this side east. Let's call this west. And he did it for a total of 10 meters. But then he turned back around and he walked 5 meters back in the direction he came. So I can ask myself, well, what is this guy's total displacement? How far did he move from this original spot? Now, considering that he went 10 this way, and then after that, he went 5 back, the question is that we're asking is, what is this position right here? And if you look at that, if he's 10 one way and 5 the other way, that means that his total distance that he moved was 5 meters. Therefore, his displacement equals 5 meters. And what's also important, since the displacement is a vector, I must also indicate the direction. So I know that he was heading east. So it'd be 5 meters east. So he's 5 meters east of where he was before. What I just did there is that with vectors, you can add them or you can subtract them based off the direction of that vector. So it's simply just summation of that. The thing that results, the thing that is what you end with, in this case, it's this complete vector right here that I'm drawing green. Okay. And we know that that is this value, the 5 meters. This is known as a resultant. And a resultant is the sum of vectors. So we can do a whole bunch of different examples with that to make it really simple. So let's say, for instance, someone went 5 meters, then later they went 5 more meters. Then I can ask, well, what's the resultant for that particular situation? And we're going to still call this east. And I would say, well, wouldn't it be this right here? And it's still going east. And wouldn't that distance be 10 meters east? So the resultant of this case would be 10 meters east. So if the vectors are going in the same way, I simply add them. If they're going in opposite ways, like this situation over here, then I subtract the vectors. And that's a really easy concept. And I can figure that out for any addition and subtraction. It doesn't matter which way it's going. So I can say someone threw a ball up in the air this way, and it went a total of 20 meters, but then it went back down and got stuck. Let's say it got stuck on a roof or a building. So here's my building right here. And it got stuck on that building. And what if I told you that that building was 14 meters tall? Then I can ask you, well, what's its displacement? And in that case, I add up 20 and I say, how far did it go down? In this case, it has to go down 6 meters. Okay. So my resultant is 14 meters up. And because that's relative to its starting point, which is down here. Okay. That makes sense. So that part is a really simple aspect of how we add up vectors to find simple resultants. This can get a little bit complex. I will talk about that aspect inside of a different video. Thanks for your time.